All right, two more big topics for Unit 10. And I have this one, I have the revealer up right now because we're going to be filling in the Vsepr chart on page 14. Okay, so you're on page 14 and we're going to start filling in this chart. All right, so you need to know all of this by heart. A lot of this is stuff you learned back in first year chem, and then there's some new stuff. All right, so we're going to be looking at these main things. So the electronic structure is called the family. This is looking at how the atoms in a molecule are actually arranged around the central atom. We're going to be talking about bond angles. We're going to be talking about polarity, stuff like that. You just have to memorize this. I do have a Quizlet made of all of this stuff, and my Quizlet link is on Vision, and you do not need to be like my Quizlet is public is what I'm trying to say. Like, you don't have to be logged in, you don't have to make an account, anything. All right, so use that to help you memorize, make flashcards, whatever. Okay, so the electronic structure is the family. The molecular structure is called the geometry. So these are like the actual like shape names. The electronic structure or the family just really has to do with the number of bonded areas. So you'll see within the same family, the number of bonded areas is going to be identical for all of them. And back up. For each family, the areas of electron density are going to be identical for all. The bonded areas plus lone pairs will add up to the areas of electron density. Something else that will be identical for all members of the same electronic structure family is going to be the hybridization. And my last video that I'm going to make, the one after this one, will be about hybridization. But for now, just fill the chart in, okay? So the first family we're going to look at is the linear family. And your chart has more space for writing. But the linear structure, the linear family, only has one molecular geometry, and that's also called linear. In the linear family, we have two areas of electron density. We're going to have two bonded areas and no lone pairs on that central atom. The bond angles there are 180 degrees. The molecular polarity is nonpolar, and the hybridization is sp. Just fill this in for now, and then the next page, we're going to start looking at the different pictures. And this is the type of stuff where it will be very beneficial, and I'll definitely make sure to go over this in class after spring break, but to actually look at the models for these things, using the model kits. And something I meant to say before, but Vsepr stands for valence shell electron pair repulsion theory. Valence shell electron pair repulsion theory. So it's called the Vsepr theory. Okay, so it's all about how these electron pairs arrange themselves around the central atom to minimize repulsions. All right, our next family is the trigonal planar family. And we have two geometries here, trigonal planar and bent. All of the molecules that have a trigonal planar shape have three areas of electron density. For trigonal planar geometry, it's 3 and 0, and for bent, it's 2 and 1. Oh wait, you actually already have all those numbers. The bond angles for trigonal planar geometry are 120, and for bent, it's a little less than 120. Trigonal planar, typically they're nonpolar. Bent, they're polar. And the hybridization is sp2. Again, I'll talk about what hybridization means later. The next family, and for right now, I just want you to fill in this stuff in. This will make a little bit more sense once we start talking on the next page. So we've got tetrahedral here. Tetrahedral has three geometries: tetrahedral, trigonal pyramidal, and bent. The tetrahedral geometry has no lone pairs. Its bond angle is 109.5 degrees. It is typically nonpolar. Trigonal pyramidal has one lone pair and three bond pairs. Its bond angle is less than 109.5 degrees. It's actually right around 107 degrees. And this is polar. And then bent, this is with two lone pairs and two bond pairs. It's like water. its bond angle is really less than 109.5 degrees. It's really right around 104.5. And that's going to be polar as well. And all of these have sp3 hybridization. Actually, okay, I'll show it to you, whatever. Tetrahedral, trigonal planar, and linear are things you learned back in first year chem. Trigonal bipyramidal is something that's new. That is something that we teach at the AP level, but we don't necessarily teach it at the academic level or the research level. So trigonal bipyramidal is going to be where you have 5 areas of electron density around that central atom. This is going to be for ones that are expanding their octet. We have 4 different geometries here. Trigonal bipyramidal, seesaw, I know it's a funny name, T-shaped, and linear. And each of these we're just adding a lone pair and changing one of the bonded areas to a lone pair. Excuse me. In trigonal bipyramidal, we have 2 main sets of bond angles, 120 degrees and 90 degrees. So for seesaw, those 2 bond angles are going to be a little less than 120 and a little less than 90. T-shaped, it's just really less than 90. And again, this will make more sense once we start looking at these structures. Linear is going to be 180 degrees. So typically, trigonal bipyramidal is nonpolar, seesaw is polar, T-shaped is polar, and linear here is nonpolar. And this has asterisks. I'll talk about that in a moment. All of these have sp3d hybridization. And then our very last one, let me just go ahead and remove the revealer, is octahedral. This is for molecules that have 6 areas of electron density around that central atom. So this is also going to be for molecules where that central atom expands its octet. We have octahedral, square pyramidal, and square planar as our individual geometries. So octahedral, all of those bond angles are going to be right at 90 degrees, and that's a nonpolar molecule, typically. Square pyramidal, the bond angles are going to be a little less than 90, and that's polar. And then square planar, those bond angles go back to 90 degrees, and that's a nonpolar, again with those asterisks. Hybridization for all octahedral molecules is sp3d2. So a couple notes. One, this chart is filled in based on the assumption that everything attached to the central atom is the same, meaning all atoms attached to that central atom are identical atoms. They're all fluorines, they're all hydrogens, whatever. And so that's in terms of the molecular polarity. So when we're talking about these symmetrical molecules, like we were talking about in the first video from this unit, if they're all the same and it's symmetrical and there's no lone pairs on that central atom, then it's an even distribution of the electrons. Even if the bonds are polar, those overall, the polar bonds cancel out. But if we have different types of atoms attached to the central one, the molecule automatically becomes polar. So that's why when I was saying, like, linear is typically nonpolar. Typically meaning when all of the atoms attached are the same. Another note, my double star, general rule is if there are any lone pairs on the central atom, then the molecule is polar. The 2 big exceptions to that are the linear from the trigonal bipyramidal family and square planar from the octahedral family. And we'll see that when I show you the structures and in class when I actually show you the models. Okay, the models they're all 3-dimensional, so it's hard to demonstrate on paper, but I'm going to do my best here, okay? This is mostly just memorization. Okay, so get to memorizing. All right, so let's take a look at a few of these. So we're going to look at every single one. On my page, I actually divided these out. So it kind of goes down linearly or horizontally down your page. All right, this first one we're going to look at, the family is linear. My central atom is what's in pink here, and my connected atoms are in white. So this is a linear family. Its shape, or its geometry, is also linear because that's the only option. Notice that the bond angles here are 180 degrees. And this is a non-polar molecule. So we're just going to be filling these in. I'm going to separate these two to make it a little bit clearer. The family represented by these two structures, for both of these we have a central atom with three things attached. Here we have a central atom with two atoms attached, and it's kind of hard to, can't really represent it here, but there's a lone pair of electrons on that central atom for that second structure. So the family here is trigonal planar. So all of these, the family is trigonal planar. This shape, this individual geometry, is also trigonal planar. So I'm just going to abbreviate that, trig plan. Now within each family, did you notice how the first molecular geometry had the same name as the family name? So whenever you have no lone pairs on that central atom, the geometry is the same as the family. It's when you start adding lone pairs, when you start moving bonded pairs to be lone pairs, that the shape changes slightly. So this is trigonal planar. The bond angles between these atoms are 120 degrees and typically nonpolar. Again, unless all those atoms connected are not the same. This one is called bent, has a bent geometry. The bond angle here is a little less than 120 degrees because that lone pair actually takes up a lot of space, that it squishes these atoms, these white ones, a little bit closer together, so that's why the bond angle decreases. And all of these will be polar because that lone pair makes it polar. And this is not one of the weird exceptions. Okay, I'm going to separate these out. All right, this entire family is the tetrahedral family because all of them have 4 areas of electrons around them. This one, it's missing lone pairs. And this one's actually missing 2 pairs of lone pairs, which you wouldn't really know from these structures. But remember, you're going to be drawing these from the Lewis structures. You're going to draw the Lewis structure to then figure out the shape. All right. So this first one, let me separate these. There we go. This first one, the geometry is tetrahedral as well. The bond angle here is 109.5 degrees. And these are typically nonpolar, unless not all of the atoms connected are identical. The second one, the geometry is trigonal pyramidal. And this is going to be polar because there's that lone pair. That lone pair squishes the bond angle to be less than 109.5. I'd said on the previous page that it's right around 107, but I don't need you to memorize 107. I need you to memorize that it's less than 109.5. And then this last one, my geometry is bent. And it's bent with 2 lone pairs versus bent with 1 lone pair that we saw last time. And this is polar as well. Those 2 lone pairs really squish down this bond angle to be really less than 109.5. Again, I told you that it's right around 104.5, but you don't need to memorize that. You need to memorize the 109.5, and then the less, and then the really less. So less, and then less. All right, all of these, my family is trigonal bipyramidal. So let me try to separate these out as best as possible. And then, so this one is my original with no lone pairs. My bond angle between these two is 90. And then here is 120. Kind of hard to see that. But so that's why we have 2 bond angles going on. And the geometry here is trigonal bipyramidal. And this is going to be typically nonpolar. This next one over, we replaced one of those bonds to be a lone pair. Okay? So that makes this bond angle here less than 90, and this one less than 120. That geometry or the shape name is seesaw. And these are polar. That lone pair makes it polar. This one, we have two lone pairs that's squishing that bond angle down to really less than 90. And this geometry is T-shaped. See how it looks like a T. And this is going to be polar as well. And then this last one is, notice how that's linear. That looks just like the first linear we looked at, but there's actually 3 lone pairs here. So the geometry is linear. The bond angle is 180 degrees. Those lone pairs are all evenly distributed around the central atom, which is why this is nonpolar. That was that weird exception. It's nonpolar, even though there's lone pairs, they're all evenly distributed. And then the last set is my octahedral family. So my first one, all of these bond angles are 90 degrees. This geometry is octahedral. And these are going to be nonpolar unless we don't have all identical atoms attached. This one, we have a lone pair down at the bottom. That lone pair squishes the bond angle down to less than 90. This is going to be my square planar. Nope, my square pyramid, sorry. Square pyramidal, and this is going to be polar. And then this last one has 2 lone pairs on the top and on the bottom. These bond angles, because they're being evenly pushed by both lone pairs, go back to 90. So this geometry is square planar. See how those are within the same plane? Planar, AR. And this is going to be nonpolar, which is another exception because those lone pairs are kind of canceling out. Okay, so that's going through those. Let's do some practice problems with this, okay? So, true or false? True or false? A molecule that has polar bonds will always be polar. The answer to this is false. Okay, it is false. And the reason why is something that has polar bonds that can be, a molecule can have polar bonds that cancel out, which makes the whole molecule nonpolar. An example is carbon dioxide. I'm just going to do the double bonded. If you ever went through and calculated the formal charges for carbon dioxide, you would find that this one, all of those have a formal charge of 0, so that is the most stable Lewis structure. Excuse me. So both of these bonds are polar towards the oxygen, but because they're pulling in opposite directions the same amount, they cancel out. So the whole molecule is nonpolar. So this is a molecule that has polar bonds, but they cancel out, making it a nonpolar molecule. My next example is, excuse me, my next question is, lone pairs make a molecule polar, true or false? And back in first year chem, you would say the answer to this is true. But now we know of a few exceptions in where lone pairs actually do not make the molecule polar. So this is false. This is not always true. So a counterexample would be any molecule, a molecule with a square planar or linear from the trigonal bipyramidal family shape or geometry. Anything like that. And a common example of this is XEF4. We already drew this before. That rhymed. We already drew this in a previous video, so let me just redraw that. XEF4 has 36 electrons that we have to fill in. So I'm just kind of going through, filling in, single bonding the fluorines to my xenon. And then we're going to have those two extra lone pairs that go back on the xenon. So the way that we would actually draw this Vsepr structure, which you don't actually have to draw Vsepr structures, you don't have to show it as a three-dimensional shape, you just have to be able to explain what the shape would be based off of the Lewis structure. But this Vsepr diagram would look like this. This is how we would represent it. We'd put the lone pair on the top and the bottom, and then this. This is how we signify 3 dimensions. The dashed lines here and here are showing something that's going down into the board, into like the plane of the paper. And these wedges are showing something that's coming out towards you. So that's how we signify something that's 3-dimensional like that. Okay? And this is a nonpolar molecule because those lone pairs are canceling out. Okay? All right, I want you guys, and this is going to be one of the main things we're going to work on when we work on this stuff in class, is number 24. But I want you guys to at least draw the Lewis structures for these. Try to figure out the Lewis structures for all of these, and then figure out the bond angles and molecular polarity once you figure out the Lewis structure and the shape. So I'm going to stop this video here so I can at least record the last one before the school day ends. And that way you'll have everything ready to go for spring break. Okay? So good luck with that.